interpretation of the hat matrix and the regression diagnostics. So to begin with, we have the data of the dependent variable, the ones for constants, the independent variable, and we have the regression coefficients which have been calculated using the formula x transpose x inverse x transpose y. We've got the regression coefficients. And now I also demonstrated how the hat matrix is calculated. The hat matrix formula is x into x transpose x inverse x transpose. So you get a hat matrix, and we also resolved that it will be a 20 by 20 matrix, which we have obtained over here. But the important thing in the hat matrix is a diagonal element. So I've taken the first diagonal element and have taken the second diagonal element, because it's the HII. So this is the HII. These are the diagonal elements. When you add up the diagonal elements, you will get the number of parameters in the regression. So if you add up the elements of the hat matrix, you get 5, which is the number of parameters in our regression is 5. So in addition, we calculated the error, the studentized error, the standardized error, the studentized error, the Cook's D. The Cook's D is also calculated using the formula 1 by P into studentized residual, which is referred to as R raised to the power of 2 into HII, that is the element of the hat matrix, HII divided by 1 minus HII is a D, and the defits, which is also calculated as the studentized residual into square root of HII divided by 1 by HII. So now we have the various parameters, and we have calculated the hat matrix, and now we go for the interpretation. Now, when we change the dependent, let's assume that the dependent variable is now changed. It's an outlier, and we get it as 25. The actual value is 5. By mistake, it has been entered as 25. Now, this will show up in the standardized residual. The studentized residual and the standardized residual and the error terms identifies the outliers in Y. So if you find large values, in the error, either the error, the standardized error, or the studentized error, it's an indication that there is an outlier in the dependent variable. It does not show up in the hat matrix. Hat matrix for the so this is the value, corresponding value. It does not show up because it is the 8th value. 1, 2, 3, 4, 5, 6, 7th, 8th value. And there is absolutely nothing in the hat value, because hat's value 1, 2, 3, 4, 5, 6, 7, 8. There's nothing visible. So the outliers in Y are identified from the standardized residuals corresponding to 10. So you get it from the standardized residual, the error term. So error term, abnormally large error terms or abnormally large standardized error or the studentized error. All three indicate. The defits indicates what is the effect of deleting that variable. It says it will have a significant effect on deleting that variable. Now, how is the defits read? The defit is calculated using this formula. The defits is a number of standard deviations that the fitted value Y changes for the ith if the ith observation is removed. An observation is deemed to be influential if the absolute value of defits is greater than 2 into k plus 2 minus 2. So we'll just analyze this. K is 5 plus 2, 7. 7 divided by, this is 20 minus 5, 15, 15 minus 2, 13. So 7 divided by 13, square root of that into 2. So I'll just, so 7 square root of 7 divided by 13 into 2. That is a formula that we have. The value should be more than 1.46, and 1.46 says deleting this variable is necessary because it has an influence on the parameter estimate. Now we'll remove this. I will undo this with a Control Z and then change this. Okay, the 10th observation. Now I'll make this 25. I'll make this 25. Now we are now talking about the influence or the effect of the independent variable, changes in any one independent variable on the correct. It has made a very significant difference. The diffits is giving us a value of 6.99, which shows that deleting of that variable will change, will have an influence on the results. But more importantly, we should look at the 8th observation in the HII matrix. The HII matrix is the one that identifies outliers in the independent variable. 1, 2, 3, 4, 5, 6, 7, 8. Now here you find the value is very large, it's 8.5. So it's an indication that there is an outlier in X, and if that outlier is removed, it will make a very significant difference to the result. It will make a significant difference to the result, and it has a very significant influence on the outcome of the study. Now I will take another value and maybe change it here and make it 40 by mistake, assuming that's an outlier, and I go down all the way. It's visible in the residuals, and you can see that the error L onwards is the error. So its outliers in Y can be detected from the error, the standardized error, and the studentized error. The difference tells us there is going to be a significant effect on the outcome, or there is going to be an influence because of the deletion of that variable. There is nothing visible. That's the last but 1, last but 2. So there is nothing visible in the diffits. Sorry, nothing visible in the hat matrix. That is there. Nothing visible. So now we are clear in our minds that changes in the dependent variable have to be detected using the changes in the dependent variable. No, outliers in the dependent variable have to be detected using the error, the standard error, the standardized error, and the studentized error. That brings us back to this slide digression. Now here he says all leverage points are not influential. Now both the leverage points that we found were influential, as it made a significant difference in the leverage score. Therefore, we take recourse to the hat matrix. The hat diagonal examines only the location of the observation, the X space. So it tells you which row in which row the error in the X is available. So we can now look at the studentized residuals or the R student in conjunction with the HI. So observations with large HII, that is diagonal in the hat matrix, and a large residual is likely to have an influence. The Cook's difference measure is a deletion diagnostics, and it measures the influence of the I's observation if it is removed from the sample. So now for this example that we just did, we will now change this to 25. So 25, we straight away look at the influence. It has an influence, so it will affect the result. It will affect the result. It will affect the result. And the last value, and here it is visible. It is very much visible in the HII. So you see, it's a relative large value. It gives a large value of HII. So we are going by the rule book. A large hat diagonal and a large residual is indicative of influence. A large hat diagonal, this is actually the diagonal which we are just transcribing over here, and a large residual indicates the. So in this fashion, we can identify outliers in data. So programs, of course, do it for us, but yet you should know the theory. So here we are just trying to explain to you what is the theory of detecting outliers using the hat matrix, the error terms, the standardized residuals, and the studentized residuals, while at the same time showing you how each one of them are calculated.